Hello again, and today we're going to take a look at changing state. So just as a reminder, if we were heating a pure substance, we would increase its kinetic energy and then increase its potential energy, then increase its kinetic energy, then increase its potential energy, then increase its kinetic energy. So realistically, it does have these slight curves here, but when we model it, because physics is all about modeling, we make straight lines connected up together. So the last lesson we took a look at increasing the kinetic energy, or talking about the particles moving faster, and today we're just looking at increasing the potential energy, giving the particles the ability or the potential to make bonds. So we're breaking some bonds here and we're breaking some bonds there. And like we said while looking at that graph, when we're heating something, that heat or that energy is going to increase the internal energy. And in order to increase the internal energy, it's either going into the kinetic energy of the particles or it's going into the potential energy of the particles, which is due to the bonds. We never have energy going into both of those simultaneously. So we've got our internal energy is all of our kinetic energy of all the particles plus the potential energy due to the bonds. And today we're just going to have a look at this side of it, potential energy due to bonds. So when we increase the potential energy, all we're doing is breaking some of the bonds between the particles, not all of them, some of the bonds between the particles. And that's changing the state of the material. And when we break those bonds, it gives them the potential to make bonds, which is why this is a potential energy. That being said, when we try to describe it, we just say that we're breaking bonds. So we don't talk about having the potential to make bonds. That's just a good way of understanding what's going on. Increasing the potential energy breaks bonds. Now, depending on the GCSE physics that you did, you might know this equation, or you might have come across it when you were reading extra stuff. Have a little think, pause the video, have a little think if you know that equation, but don't spend too long on this one. So the equation for changing state is Q equals mL, where Q is the energy or the heat added to the system, measured in joules. M is the mass of the system in kilograms, and L is the specific latent heat, and we'll go through the units in a second. Make sure you get this equation into your notes with what each of these variables is and their units. Leave a space for the units on L so you can come back and put those into your notes. So as we did with the specific heat capacity, we're just going to go through each of those variables inside the equation and take a few little notes on each of those variables. So Q is the amount of energy added to the system. It's measured in joules, but occasionally we give it in kilojoules because we can be dealing with rather large amounts of energy. And there is a sign notation with Q. This is exactly the same as the specific heat capacity sign notation. If heat is being added to the system, so we're breaking bonds, which is either melting or boiling, then Q is positive. If energy is being removed from the system, so we're making bonds, which means we're either condensing or freezing, then Q is negative. And this sign convention, just like our specific heat capacity sign convention, ensures that it can correctly be used with the first law of thermodynamics. So this is probably something that you want inside your book. If you want to link it to specific heat capacity, you're more than welcome to. If we're adding heat to the system, then Q is positive. But remember, this doesn't mean increasing temperature. This means increasing potential energy, so we're breaking bonds. If we're removing energy from the system, or we're forcing those particles to make bonds, then Q is negative. And this kind of goes along with our definition of Q, that it's the amount of energy added to the system, and that's where we get our sign notation. So adding is a positive Q, and then doing the opposite of that is a negative Q. We have the same sort of notes on M as we did for our specific heat capacity. So lowercase m is just the mass of the system, and inside our equation that has to be measured in kilograms. Now oftentimes we're given that in grams, so do watch out for the conversion factor, be really, really careful with that. I'd probably put like a little star asterisk or somewhere around the units or highlight the units for M. Make sure you convert anything given to you in grams into kilograms. That capital L is called the specific latent heat. I want you to take a moment and try to rearrange that equation for capital L. So rearranging the equation, you should get capital L equals Q over M. Now I want you to try to take that equation and turn the math speak into English. So the specific latent heat is the amount of energy required to change a mass of 1 kilogram to a different state. And if this was on your GCSE, this is probably the definition that you used. However, this is an absolutely lousy definition of the specific latent heat when we come to A level, because we've got so much more knowledge than just that. So don't write that definition down in your books. That is potentially a GCSE definition that you know. It's not wrong, it's just very, very basic. And we'll come back to that in a moment. But first, let's take a look at the units. So using that rearranged equation, I want you to try to come up with what you think the units for the specific latent heat is going to be. Hopefully you said joules per kilogram, which would be correct. However, they can also be given in kilojoules per kilogram or joules per kilogram. Note that these two units are exactly the same thing. So if we've got a kilojoule per kilogram and we decide that we're going to convert joules or kilojoules into joules, we'd end up with 1,000 joules over 1,000 grams, and then those thousands cancel out. So a joule per gram and a kilojoule per kilogram are exactly the same thing. But as you can see, it's 1,000 times that, which means that it's really suitable when we're dealing with large energies. So L is used for state changes, but we've got two very different changes of state. Below we've got a triangle showing the 3 different states, and the arrows represent changes between those states. I'd like you to pause the video and give a try at labelling all of those arrows. Hopefully you have a solid to liquid is melting, liquid to solid is freezing, liquid to gas is evaporation or evaporating, not boiling. Boiling only happens at a particular temperature. And gas to liquid is condensation or condensing. Solid to gas is sublimation, gas to solid is deposition. And for the purposes of pretty much the rest of thermal, we assume that we're dealing with regular sort of atmospheric pressures and that we can just ignore that side of the triangle. So because we have these two very different state changes, we've got melting and freezing, and then we've got evaporation and condensation. So we're going like between a liquid and a solid, or between a solid and a gas. We've got two very different definitions for L, or specific latent heat. Now when we go from a solid to a liquid, we're breaking bonds, we're putting energy in to break those bonds. And then if we were to go from a liquid back to the solid, we would get the same amount of energy out as it remade all of the bonds that we just broke. So we group melting and freezing together, and the two of these together we refer to as fusion. Similarly, we group evaporation and condensation together, and we call these vaporization, which I'm not going to be able to spell while I write. Okay, so there's no U in there, just vaporization. And we're going to have a look at fusion first, so going from a solid to a liquid or a liquid to a solid. So the specific latent heat of fusion is the amount of energy required to change a mass of 1 kilogram from a solid at its melting point into a liquid at the same temperature. Now this is a good definition for specific latent heat. Notice that it specifically states what state changes we're going through. We specifically specify fusion, and we differentiate that from vaporization. So the specific latent heat of fusion has its own definition. And it doesn't matter if we're dealing with solid to liquid or liquid to solid, we're always dealing with fusion for that state change, liquid to solid, solid to liquid. And again, this definition is always written as solid to liquid because that's the state change that requires energy. This definition is always written as the amount of energy required. So we need to specify solid to liquid because that's the way that we require to give the system energy. So using this definition of the specific latent heat of fusion, I'd like you to take a moment and try to determine the definition for the specific latent heat of vaporization. Pause the video now. Hopefully all you've done is replaced those words in bold with ones that make sense for vaporization. So you have the specific latent heat of vaporization is the amount of energy required to change a mass of 1 kilogram from a liquid at its boiling point to a gas at the same temperature. And again, just like the fusion definition, we deal with the specific latent heat of vaporization, regardless of if we're going liquid to gas or gas to liquid. And this definition is always written as a liquid to a gas because it's always phrased as energy required, and liquid to gas is when we require energy. Now, most of the time I tell you guys not to memorize definitions. This is one of the times, and just get it from the equation, this is one of the times that I'm going to say, if you want to memorize it, you can, or if you want to use it from the equation, you can. But if you're going to do it from the equation, there's a few things to remember. So our definition of specific latent heat, regardless of fusion or vaporization, always is dependent on that equation. It's energy added to change state per unit mass, or per 1 kilogram, at a constant temperature. And it's really important that we have all three of those bullet points in there. We then need to add in the extra detail. Your exam will never ask you to define specific latent heat. It'll always say, just define specific latent heat of fusion, or define specific latent heat of vaporization. So that should be a little key to yourself, that you need some extra detail as opposed to just the equation for specific latent heat. Since energy is always added in our definition, the state changes are always solid to liquid if we're talking about fusion, or liquid to gas if we're talking about vaporization. So pause the video now and take this time to either get both of those definitions into your notes and ways of remembering them, or get an understanding of how to put those definitions into your notes to remember them. So if you want to put like the word that's in bold as a blank, and then you can fill in the blanks with either fusion or vaporization, solid or liquid, liquid or gas, so on and so forth, however that makes sense to you. So despite their names, specific latent heat of fusion and specific latent heat of vaporization, the specific latent heats for a substance are completely unrelated. So here we've got aluminium, water, carbon dioxide, gold and lead, and they're in order of their specific latent heat of fusion from highest to lowest in kilojoules per kilogram. And then if you look at the second column, or third column technically, you see specific latent heat of vaporization. You'll notice that there's no pattern to those whatsoever. So these two specific latent heats for one substance are completely unrelated. Like the specific heat capacities, you're not expected to know these values. You will be given them if you need them inside an exam setting, but you should have a good understanding of whether or not your answer is reasonable. So for specific latent heats of fusion and vaporization, sort of tens to hundreds is a good order of magnitude. Water is a little bit bizarre going from water to steam, in the sense that it takes a buttload of energy to get liquid water to turn into steam. And we can see that because the specific latent heat of vaporization of water is absolutely massive. So if you do calculate a specific latent heat of vaporization that's a few thousand, that could be correct, but that is taking absolutely loads of energy. And so you probably just want to double check through your maths. Alright, so we're going to go through 4 examples. And what I'd like you to do is when you see a new example, pause the video, give it a try, either on scrap paper or inside your notes so that you can see what you've done later, and then play through the video and double check your answer. So pause the video now. Alright, so how much energy, it's asking us what is Q, would it take to melt 20 grams, there's our mass, but remember we want to convert that into kilograms, of gold. So we want gold at its melting point. So we need to be mindful that we're trying to melt something. We're going from solid to a liquid. So that's using fusion. So the specific latent heat that we want to use is this one here, the specific latent heat of fusion. I personally like to use subscripts, like a little F here, so that I know I've double checked it is fusion. Your exam may try to trick you by giving you both the number for fusion and the number for vaporization. That has happened before. So I'm savvy to that trick. I've written my little F. I know that it's fusion that I want. 110 kilojoules per kilogram. And then I write out my equation, Q equals ml, and plug my numbers in, 0.020 and 110, and I get an answer of 2.2. Now be careful with units here. We've got a kilogram and a kilogram, so those two cancel each other out. And then we've got a kilojoule left over. So this is actually 2.2 kilojoules rather than just a regular joule. So it's 2,200 joules. Example number 2, pause the video and give this a try. So how much energy, again asking about energy, would be released if 100 grams, need to convert that into kilograms, of molten lead solidified. So we're talking about liquid to solid. So we're talking about fusion again, without a change in temperature. So this is the one that we want. We want the specific latent heat of fusion, which is 25 kilojoules per kilogram. We're writing in our equation Q equals ml and plugging our information in, 0.100 times 25, putting that into our calculator or your mental maths, and we get an answer of 2.5 kilojoules. Again, being careful with that unit that we've got kilojoules in our specific latent heat of fusion there. Now, technically speaking, this one is going from a liquid to a solid, which means it's releasing energy. If we're releasing energy, we should have a negative sign in there and we should have a negative sign in there. But your exam isn't too fussy with this. Again, with the language, how much energy would be released? Well, positive 2.5 kilojoules would be released. But if you were to want to combine this with other things, such as the first law of thermodynamics, when you go on into like higher education, if you come across anything like this, you definitely want this Q value to be negative because it is giving off energy. And the way that we do that is if we're going sort of liquid to solid, if we're releasing energy, we call that latent heat a negative value. And it is just whatever value it is when you plonk a negative sign in front. For the purposes of your A levels, you don't need to worry about that at all, and we don't need these negative signs at all. But for the purposes of going on and, maybe doing some sort of engineering, that's probably something that you want to keep in mind. Example number 3, pause the video and have a go. So a hunk of aluminium at its melting point, so that kind of gives us an idea that it's going to be fusion here, takes 1,650 kilojoules to become liquid. Yeah, definitely fusion there. So we're dealing with the latent heat of fusion. What is the mass of the hunk? So we want to write out our equation, Q equals ml, and then rearrange for m. So we have m equals Q over L. Then we want to substitute our numbers in. So we've got 1650 over 660. And really this should be on the next line. We should be working vertically and not horizontally here. I'm just running out of space. And we get m is 2.5 kilograms. All right, last example. Pause the video, give it a go. All right, a pot of water initially has a mass of 2,500 grams. After boiling for a while, it has a mass of 2,350 grams. how much energy went into making steam. So they are asking us about how much energy, and at first this might look a little confusing because we're given two masses, and it's specifically asking us about a pot of water, so we're talking about the water there, and making steam, so that's going to be vaporization. So we are specifically looking at the specific latent heat of vaporization, put a little V there so I know it's vaporization, 2,300 kilojoules per kilogram. But it's given us two masses, and it's always a good idea to kind of draw out the situation if you're having difficulties with what's happening. So initially we've got 2,500 grams of water in there, and then after some time that pot of water has just got 2,350 grams of water in it. So where'd that extra go? Well, that is the mass of the steam, and that's the mass that we're interested in, because we're interested in how much energy it took to make the steam. So we need the mass of the water that turned into steam, or the mass of the steam. Either phrasing is good. So our mass is going to be how much water we had at the start minus how much water we had at the end, because the leftover bit is how much water turned into steam. So we've got 150 grams of water became 150 grams of steam, but remember we need that in kilograms, so we've got our mass is 0.150 kilograms. And then we can plug this into our equation, so we've got Q equals ml, Q equals 0.150 times 2,300, and that gives us 345 kilojoules. Now that is loads of energy. That's over a third of a megajoule, and that's to turn not even a cup of water into steam. Water takes loads of energy to heat. Water takes loads of energy to turn into steam. So anytime that we're dealing with water, you probably will end up with ridiculously high numbers. Water takes a lot of energy. So hopefully those examples went all right for you. And we're just going to summarize what we've learned here with some key concepts. So just like our specific heat capacity video, we model heating substances as increasing the temperature or changing state. For a change in state, Q equals ml. And just like our specific heat capacity, Q is positive for adding energy and Q is negative for removing energy. And again, just like our specific heat capacity, we need to be careful with the units. So Q is often given in kilojoules. Mass can sometimes be given in grams, and that always needs to be converted to kilograms. And then L, we can have joules per kilogram, or we can have kilojoules per kilogram. Just be careful with the kilojoules. Fusion is dealing with a solid going into a liquid or a liquid turning into a solid. And vaporization is a liquid going into a gas or gas going into liquid. And we have our definition that has this form. The specific latent heat of blank is the amount of energy required to change a mass of 1 kilogram from a blank at its blank point into a blank at the same temperature. So for fusion, we have specific latent heat of fusion is the amount of energy required to change a mass of 1 kilogram from a solid at its melting point into a liquid at the same temperature. And for vaporization, we have that the specific latent heat of vaporization is the amount of energy required to change a mass of 1 kilogram from a liquid at its boiling point into a gas at the same temperature. Hopefully that gives you enough that you can give the past paper questions a try, and let me know if you have any questions. Have a fantastic day.